This is lecture 23 of CS147 Computer Architecture Study. In this lecture, we'll be studying about virtual memories, its concepts, and the implementation on the hardware. Now, single program environment enjoys entire resource of the computing system, which is not very relevant in modern days. In very old days, computers is basically it runs one program at a time, but modern computing system it runs multiple program at a time. Your laptop, if you take an example, your laptop, like you open your browser, your maybe program editor, maybe some gaming applications, notepad, all sort of application you open, right? And there apparently seems to be running in parallel with each other. That means it is a multi-program environment. Now, multi-program environment, it that means somehow we need to partition the resource usage, right? This partition can be the temporal or a spatial. Okay, the temporal means we are time sharing a resource. Okay, so for example, the processor. Though we see the like 10 or 15 different programs are running on our computer, and apparently it's running in parallel with each other, but down the line, what happens? Your operating system time slice usage of the processor per process currently running in the system. It is not that your programs are really running in parallel with each other. Of course, like if you have nowadays all systems are multi-core, and then probably if you have, let's say, four core in your processor, then possibly four programs are truly running in parallel with each other, but not really. Like 50 different programs are running in parallel with each other. They are time sharing your compute resources like processor, and they execution switch from one program to another in such a way it apparently to us as a human we perceive them as if it is running parallel. And memory, on the other hand, is a resource which is spatial distribution. Like not like let's say you have 50 different program, that means each program need to have its own memory, and your memory as a resource is a fixed resource in the computing system, and you then need to distribute the memory among different processes spatially. Like it says space allocation, almost like a space allocation problem, that you are partitioning an area and allocating the sub partition of the area to each of the like individual program who claiming that space. So this okay, so this temporal processing, this is like an managed by operating system, temporal and spatial partitioning, uh, and of course it needs some hardware assistance to do it. As I said, like these programs are scheduled in a time slice manner on the processor, and operating system manages them via context switching. Like one process takes maybe 10 millisecond of the time, and then it goes into the sleep state. Another process comes in, becomes active, using the resource for next 10 millisecond, and so on and so forth. So it is so fast that apparently to the human we see that those programmers are running in parallel. And the spatial management is done by the memory management. So this virtual memory is basically more related with the like spatial partitioning or memory partitioning. It has a two problem to solve. First of all, how to create and maintain the partition boundaries so that we know that one program we ensure that one program cannot access part of the other program. Okay. And secondly, how do we manage with smaller share of main memory? Let's say you have 4 gigabyte of main memory in your system, or maybe 8 gigabyte. Let's say you can easily run in a process. If you open the list of processes running at one time, it can easily reach 50 process. Okay, so 4 gigabyte divide by 50, so average each one will have some smaller share of the main memory, right? Now, two factors are unknown at the compilation time when you compile a program. Now, first of all, how much memory going to be available at the runtime? Depending on the target data set, your memory requirement can go up or down, right? Your program may not have a fixed amount of memory requirement, right? It can vary with the input data size. Also, which addresses are going to be available at the runtime? That's another problem because we don't know. It's a multi-program environment and completely dynamic environment. This virtual memory technique gives program an illusion of enjoying the entire memory space of the system and possibly beyond. We'll talk about that, what we mean by the beyond part. Now, all the addresses are available to a program. That is one thing it supports. And then memory space can be much bigger in size than the actual main memory. Like, let's see, if you have like 4 gigabyte of RAM installed in your system, your virtual memory can be bigger than that. Okay. So how do we implement it? So we are basically running multiple program in parallel, but we are trying to provide each of this parallel running program an illusion of giving them the entire address space that available. Okay, and also your memory space can be bigger than the physical RAM present in the system. Of course, 32-bit machine can address 4 gigabyte memory space, whereas 64-bit machine theoretically address 2 to the power 24 terabyte of memory space, which is, we can think of it's the infinite memory, okay, as a memory space point of view. The actual memory will term it as a physical memory now from now onward. So in this physical memory can include both main memory, of course, along with the cache, which resides in the processor chip, and the disk. Now we are including disk in our memory system. The main memory acts as a cache for the disk. Okay. The virtual memory mechanism automates the management of two-level hierarchy between main memory and the disk. So your cache system is basically managing hierarchies of the cache and the main memory, and virtual memory is managing memory hierarchy between main memory and the disk. Now, a part of the hard disk is used for implementation of virtual memory. Like if you ever install like Linux or some equivalent operating system, it asks for some swap space allocation. The swap space amount determines how much would be your limit of the virtual memory. So, of course, virtual memory has a limit of its own, but with the allocation of right amount of swap space, your program can enjoy whatever it needs. Of course, it cannot be infinite in theory because it's all physical resource. But its illusion we can give that it is at least enjoying the entire memory space for a 32-bit system, at least entire memory space, that all the addresses which can be generated by the processor. It can use it. It's one single program, though it isn't running in a multi-program environment. The virtual memory is similar to cache. Main memory act as a cache for the disk, and both this virtual memory and the cache memory exploit locality of program execution. Remember, we had this temporal locality and the spatial locality. It this virtual memory scheme works because software has those locality properties. Now, in this case of virtual memory, blocks are called page and miss are called page fault. Okay, so what happened? Your cache memory evolved from hardware engineer and design side, whereas virtual memory evolved from the software engineering side. So their terminology is different, become different, but concept wise, they are practically same concept. So instead of like replacing, we call a replacing a block in a cache memory. In virtual memory, we'll call replacing a page. Okay. Now, processor, what processor issues is a virtual address. Okay. And then it get translated into physical address. There is address mapping of the translation happens in this system. And it also provides a relocation facility for a program execution, because like your program, software program is operating on the virtual address, which means is the entire address space is available to it. And this virtual address then gets mapped into a physical location, physical memory address that goes and seeks data from the real memory device. Now, if you think that if we actually change the map from virtual address to the physical address, we can actually start relocating from one place to another into the physical memory if needed. Right? What we all need to do is to change the map from virtual memory address to the physical memory address.